Hello. Hey, thanks for the introduction. So hello everyone, my name is Shin-Yeh Tsai from Purdue University. So today I'm going to talk about our project, Pythia, Remote Oracle for the Maces. So this is a joint work with Professor Matthias Peer from EPFL and my advisor Ian Zhang from UCSD. So let me start my talk by discussing data center a little bit here. So data center security is really important, especially more and more data are processed and managed within a big data center in the last few years. So data center has been the place of attack, and it's really important to protect our data in data center. So let us take a look at what data center needs and recent trends. So data center demands faster network, large memory, and also low CPU utilizations. That's why RDMA fits this trend. So let me introduce RDMA here. So RDMA stands for Remote Directly Memory Access. So in comparison with traditional classic communications, the classic communication goes through the user space applications and trap into kernel, and the request arrive at the remote side, it will be processed by the CPU and back to the memory again. So in RDMA, the request is issued from the user space application, go through the library and interact with the hardware directly. When the request arrives at the remote side, it will access the memory directly. Therefore, no longer kernel and CPU are involved in RDMA. So with RDMA, this design can read and write remote memory. It bypasses kernel at both local side and remote side. Finally, it offers memory zero copy. Because of this design technique, RDMA offers low latency, high throughput, and low CPU utilizations. Because of the performance benefit of RDMA, recently more and more data centers adopt RDMA technology to improve their applications performance. For example, like Microsoft Azure, they move to RDMA, and also Alibaba Cloud, they adopt RDMA. So there are also a lot of RDMA-based data center applications in both academia and industrial. However, most of them either focus on performance, scalability, and usability. So then what about security? It's really important in data centers. So let me present you the Pythia, the first side channel attack on RDMA. So let me introduce our threat model first before I go into the detail of our design. So there are two sides in our model. The client side, which includes the victim and also an attacker. Then another side is server side. So server side holds data inside the memory and export it to users via RDMA. So the attacker and the victim can be on different machines, and the attackers want to learn the access pattern of the victim. For example, victim says get key 50, then the attackers want to know did the victim really access this key. So we assume that attackers cannot observe the network traffic from the client side, otherwise it can tell the answer directly. So now we are using RDMA, therefore all the requests will be processed by the hardware NIC, RDMA NIC. So let us look into what is inside the RDMA NIC. So we can see the classic communication first. So in classic communications, because all the requests are handled by CPU or processors, therefore requests will go into a regular NIC and pass to a CPU. Then we let the CPU do the address mapping, permission checking, and resource isolations. So because there's a massive overhead of using classic communication because CPU is involved. So in RDMA, because no longer we need CPU here, so we have a stronger RDMA NIC and also more complicated. So in RDMA, it relies on a concept which is called memory region to handle the address mapping, permission checking, and all the things. So now the card does the address translation, which is handled by CPU before. So in the memory regions, there are two main things. The first thing is R key and L key. So R key is a key which is provided to remote client to let it do the permission checking. So the NIC will check the key when the request arrives. Also, the address is used for the address translations. So let us look into this metadata a little bit more. So in RDMA NIC, there are three types of metadata. The first type is queue pairs, which handles the connections. The second type is memory regions, which does the address translation and permission checking. Finally, is page table entries. So does the address translations. Because of the time limitations, I will mainly focus on page table entries today, which is also called PTE. So when RDMA request comes in, arrives at the remote side, it includes a virtual address and a key. Then the RDMA NIC would check the keys and does the address translation and get the physical address and access the memory accordingly. So let us see this example. When a request arrives at the remote machines, it would check the NIC, check the cache, find the metadata, it's hit. Then it will access the memory. So it's really fast. It's really fast. So let us look at another example. When a request comes in, it found it's missed. So all the metadata are not inside the RDMA cache, RDMA NIC cache. Therefore, it needs to fetch from the host machine to get the PTE and other metadata. So you get it one by one. So this part creates a little bit slower. After bringing all the metadata fetched back to the RDMA NIC, it can finally access the memory. So these parts create the timing difference. This is the side channel we discover. It's a side channel. So let me introduce the Pythia. It's a set of side channel attacks that we introduce on RDMA. So the basic of Pythia is evict and reload. For example, like if we let the victim access a specific page through RDMA, it will bring the metadata into the RDMA NIC. Then the attacker evict to clean the metadata. Wait a little bit. If the victim accesses the page again, it will bring the metadata into the NIC again. Then attacker does the reload operations and time these operations. If it's fast, it means access. The victim accesses this page in the last time window. Let us look into another example. Victim access first, attacker evict. Victim access some other pages. When attacker does reload, it will be slow. It means the victim didn't access this page before. So attacker can redo this attack round again and again. Then the attacker can learn the accessing pattern of the victim. So why we do reverse engineering? Because we found out that the basic evict and reload is slow. Because now we cross the network, it's RDMA. So the basic evict and reload takes around 25 milliseconds, not 70 minutes. So after our reverse engineering, we improved the efficiency by 500 times. Now we only need 15 microseconds to do one round of Pythia attack. So now I will introduce how we did our reverse engineering. However, because of the time limitation, I will not go into detail today. So please check our paper for more details. So we suppose that the RDMA NIC cache will be similar to a CPU cache. There are sets and ways. So we use the fixed set size to find out the index bit. And we also use different eviction set size to find out the potential ways. Finally, we found out it's 8K and 128. Then we found the prefetch effect inside the RDMA NIC. When a page is accessed, it will also bring the closed metadata into the RDMA NIC, which facilitates the computation, also the access. So after this, we found out that there are 1K set. And we also found out that some of the pages, the accuracy when we use our model to evict is not that high, it's only 75%. So we found there may be another set. So we found the high index. So the metadata will either be in the set pointed or directed by the low index or high index. Therefore, in order to improve the accuracy, Pythia attack evict both sets to have good accuracy. So this figure summarizes what we discovered with reverse engineering. So this is the complete layout of RDMA NIC we observed from the experiment. So let me show you this figure. This is a this is a PDF figure which discusses the latency. So the x-axis is latency in microsecond. The y-axis is percentile. So the right-hand side is greater latencies. So we know that one RDMA request requires page table entries and also the keys to do the page translations. So if all the metadata is inside the RDMA NIC, this translation will be fast. So it will be a black line, means hit. If page table entries are not inside the RDMA NIC, it takes some time to fetch it from the host machine's memory. It will be a green line, it's a little bit slower. Finally, if all the metadata include the memory regions are not inside the RDMA NIC, we need to fetch all, then it will be yellow line. So we can see a clean separation between these three assets. So this is the side channel we discover. So this is not only in the Connect X4, the NIC that we use. We also found the same issues on the different generations of RDMA NICs. For example, like the latest available RDMA NICs from LNX, the Connect X5, we can see the same things. Even in the cloud lab, which is a public cloud, we see the same issue. Now we show that Pythia can also be deployed on real applications. Therefore, we attack a real application, which is called Apache Crail. So Crail is a research project originated from IBM, and it's a Java-based storage platform. So we picked the key value store interface and also the RDMA communication to show our Pythia attack. So how to attack Crail? So in our project, there are 3 different types of attack, different ways to attack Crail. The first way is called MR-based. So in Pythia MR-based attack, we need a helper process on the machine, which is co-located with the Crail service provider. So we let the victim access a page through Crail first. It will bring the MR metadata into the RDMA NIC. Then the attacker will communicate with the helper process to evict all the memory region metadata from the NIC. The attacker does a reload. This part leaks the accessing pattern through the side channel. Similar for the page table entry based attack, it also requires a helper process on the Crail service provider. But now we use page table entries metadata. It brings the page table entry metadata into the RDMA NIC. The helper process evicts the metadata. Attacker does a reload. This part leaks the accessing patterns. Finally, we have a client-based attack, Pythia client-based attack on Crail. So in this attack, it's more powerful than the previous 2. So now we use only the Crail client to attack. We no longer need to run any helper process on Crail machines, which is fully a remote attack. So in this attack, when victim access a page through Crail, it will bring the metadata into the RDMA NIC. Then the attackers just issue a set of Crail requests, read requests. Then it can evict the victim's access metadata. Then reload, then leaks the accessing pattern. So this is the most powerful one. So let me show you this figure. This is the same figure as what I illustrated before. It's still timing these different figures. So you can see the x-axis, the latency. Even with the Java and also application overhead, we can still see the timing difference between different assets. So this is the side channel we discovered. So based on these side channels and timing difference, we have this result. So let me show you the client-based attack result. So the x-axis is timeline in milliseconds. The y-axis is the access probabilities. So the attacker will keep predicting the access probability of victim, whether the victim access a specific page in the last time window. So we let the victim run a Zipf workload on a million pages, so through Crail. So the interarrival time of each access is based on Facebook key value store workload, the interarrival time. So the red cross means that victim access the specific page. So the black dot is the attacker keeps using the Pythia attack with client base to see whether the victim access or not. So you can see there's an overlapping between the red cross and also the black dot. This means the Pythia client-based attack can really observe the victim's accessing patterns. So we introduced the attack of the RDMA side channel. The side channel attacks on RDMA. So let me discuss how to mitigate these side channel attacks. So the first idea is to do the client-side mitigations. We can introduce noise inside the software. For example, because this is a timing channel attack, a timing difference attack. Therefore, if we put the noise inside the Crail, we can make the side channel attacks harder. This is the first idea. Second way is we do the network traffic monitoring inside at the network side. It could either be in the hub or in the switch to see are there any malicious side channel attacks requests. So finally is the server side mitigations. This is stronger than the client side, also the network side because of the overhead. So server side has lower overhead and it doesn't require, it can also avoid to use the machine which is controlled by the attacker, the client side. So at server side, we can use huge page or physical memory registration. So it means get rid of the virtual memory registrations. So this can reduce the overhead of the address translations, which can make the side channel attacks harder. So the second idea is to do the hardware resource isolations on RDMA NIC. Like what I mentioned above, in the MR-based attack and also the PTE-based attack, it requires a helper process running with the Crail machine, on the Crail machine. Therefore, if we can have the resource isolations, we can avoid these two types of attack, which can improve the security. Finally, the separate resource between different connections, and which is called protection domain. When we disclose these vulnerabilities to Mellanox, the RDMA providers, the Mellanox engineers hinted out these solutions, the protection domains too. However, we found out, as far as we know, most of the RDMA-based applications, they only use one protection domain. Because using multiple protection domains will bring the performance loss. In our experiment, we can see 15 to 25% performance overhead when you use multiple protection domains. So let me conclude today's talk. So we know the RDMA performance is really good. That's why data center engineers and also the managers, they want to bring the RDMA into data center to improve the application's performance. However, how to add the security guarantees to RDMA will be really challenging. The main issue is because there's also a trade-off between the performance and security. RDMA is attractive because of its good performance. Once we add the security guarantee, we add the overhead into the RDMA performance will be a little bit slower, where RDMA still be attractive to data center engineers when we have a little bit lower performance. This is what we need to think about and to design the whole system carefully. So thank you very much. And if you are interested in Pythia code, it will be open source on this GitHub link. So please check our website and also our report if you are interested. I'm happy to take the question now, and thank you.
Okay, so we have time for 2 or 3 questions, so please.
Anna Kornfeld-Simpson, University of Washington. Great work. I'm so excited to see some attention to RDMA at a security conference. I know that in some of the papers in the systems and networks community that they've said, oh, well, if one client that has access to the server's R key in the data center gets compromised, then game over, we don't have to care about security. Do you have so to execute your side channel attacks, your attacker needs to have R key, have access. Do you have a good answer for the folks in the other communities who are saying, oh, if they get it at all, then we don't have to care?
So are you asking about should we use one R key for all the applications, for all the users, or separate the R keys between different users?
I guess another way of phrasing might be, how did your attacker get an R key to be able to do the one-sided reads and writes to the server?
So in our threat model, because attacker is another client, so it has all the information that regular clients have. So if regular clients can access some page, it has the R key. Therefore, the attacker has the R key as other client. So it's no extra privilege for the attackers. Did I answer your question?
Hi, Joe from UC Irvine. Very interesting work. So I want to ask about the other scenarios for RDMA. I recently heard that you can do the RDMA between GPUs. So have you looked into that perspective, or do you see any security issues there?
So using RDMA to access GPU, I remember it's called GPU Direct. Yeah. So it's through the NVIDIA and Mellanox. So we didn't look into the GPU Direct so far, but we expect once these issues would happen not only in regular RDMA, it may be also happen every other place, because by design, you need to cache the metadata inside the RDMA NIC to handle all the things. But we haven't looked into the GPU Direct. It would be interesting to look at it.
Okay. Thank you.
I had one.
Okay, the last one.
I had one other question, which is, so for when the metadata gets off the SRAM of the NIC and it's slower, I assume the application developers try to avoid that since they're wanting to make the RDMA as fast as possible. Do you have any intuition for, in practice, how often the important metadata gets pushed off the SRAM?
So I didn't have the number here, but from one paper which is called FARM, Fast Access Remote Memory, it's mentioned they have a number to show what is the frequency of metadata will be moved out evicted from the RDMA NIC. So even in a regular access, not the attackers, once the memory region size is larger than 60 megabyte, and with a random access within this 60 megabyte, we can see the metadata is evicted. So some numbers can be seen in that paper, and also in the light paper in SOSP. Yeah.
Okay, I think it's time for us to enjoy the coffee break. So please thank all the speakers for the great talks.